Driven in large part by the Fourth Industrial Revolution, increasing requirements for material and chemical purity have encouraged advanced node semiconductor fabs to move away from stainless steel to fluoropolymer material for transporting process fluids. Traditionally, stainless steel has been used because of its safety with volatile solvents. As semiconductor line widths continue to shrink and process nodes approach sub-10 nanometer levels, metal contamination becomes especially detrimental to devices. Stainless steel is no longer meeting the purity requirements, so the industry is moving to PFA systems. While PFA delivers much higher purity than stainless steel, it comes with increased safety risks, particularly due to the danger of static charge generation and harmful electrostatic discharge, known commonly as ESD. ESD can be powerful enough to cause pinhole damage to components such as PFA tubing, diaphragms, or PFA filter housings. These pinholes can cause chemical leaks that can be a safety risk as well as contaminate the process. An ESD event in a PFA tube with flammable solvent could ignite the surrounding solvent-rich environment. Much as a bolt of lightning can strike in one spot and travel, creating a path of destruction in its wake, a single electrostatic discharge can have a similar effect on a semiconductor manufacturer's bottom line. In our test lab, we can create a charge building within the media and on the surface of a PFA fluid system. Let's take a look. Some solvents have low conductivity, which enables them to generate and accumulate an electrical charge. When these solvents are transported in standard PFA tubing, the non-conductive nature of the tubing, combined with the low conductive property of the solvent, increases the risk of electrostatic charge buildup within the liquid, PFA tubing walls, and other PFA components. In this setup, we will run DI water and nitrogen through a standard PFA system. Using a static field measurement tool, we will measure static potential on the surface of the tube. We will also be measuring the amount of static charge that builds in the media itself by using a Faraday cup. As the voltmeter shows, static builds quickly through the system as well as in the media, as shown by the meter connected to the Faraday cup. We even see sparking as static charge continues to accumulate. Accidents caused by uncontrolled ESD can have grave consequences, including the loss of life as well as millions of dollars in property damage. Now imagine a fully conductive system designed from a new material that removes charge from the media as well as from the components. The PFA tubing has carbon stripes along the inside, and the fittings are carbon loaded to create a path to ground when the sealing area of the fitting contacts the conductive stripe. The new approach removes the charge from the media, reduces required ground wiring, maintains the integrity of the PFA tubing, and allows an uninterrupted path to ground throughout the entire fluid circuit. This system has proven to successfully reduce the accumulated electrostatic charge from both the media flowing through the tubing as well as any charge that might build inside or outside the tube. Entegris is working very hard to innovate in chemical delivery system components and materials to find opportunities to eliminate ESD risks from potentially volatile processes altogether. We look forward to innovating alongside semiconductor and equipment manufacturers worldwide to mitigate safety risks and yield loss in all of your processes.